Hello. All right, back at it. So where did we leave off? We've got a neural network that we've written that can support an input layer, a sigmoid layer, and 3 different types of output layers. Sigmoid with a quadratic cost function, sigmoid with a cross entropy cost function, and softmax with a log likelihood cost function. And they all work pretty similarly. Softmax might be slightly better. Actually, I don't know which one is slightly better. They're all pretty similar. Within 30 seconds, they can be trained up to be 95% accurate. Within 1 second, they can be trained to be 90% accurate. So pretty cool. We're learning tricks to learn better, and let's keep going with overfitting and regularization. The Nobel Prize-winning physicist Enrico Fermi was once asked his opinion of a mathematical model some colleagues had proposed as the solution to an important unsolved physics problem. The model gave excellent agreement with experiment, but Fermi was skeptical. He asked how many free parameters could be set in the model. 4 was the answer. Fermi replied, "I remember my friend Johnny von Neumann used to say, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk." The point, of course, is that models with a large number of free parameters can describe an amazingly wide range of phenomena. Even if such a model agrees with the available data, that doesn't make it a good model. It may just mean that there's enough freedom in the model that it can describe almost any data set of the given size, without capturing any genuine insights about the underlying phenomenon. When that happens, the model will work well for the existing data, but will fail to generalize to new situations. The true test of a model is its ability to make predictions in situations it hasn't been exposed to before. Fermi and von Neumann were suspicious of models with 4 parameters. Our 30 hidden neuron network for classifying MNIST digits has nearly 24,000 parameters. That's a lot of parameters. Our 100 hidden neuron network has nearly 80,000 parameters, and state-of-the-art deep neural nets sometimes contain millions or even billions of parameters. Should we trust the results? Let's sharpen this problem by constructing a situation where our network does a bad job generalizing to new situations. We'll use our 30 hidden neuron network with its 23,860 parameters, but we won't train the network using all 50,000 MNIST training images. Instead, we'll just use the first 1,000 training images. Using that restricted set will make the problem with generalization much more evident. We'll train a similar way to before using the cross-entropy cost function, with a learning rate of eta equals 0.5 and a mini batch size of 10. However, we'll train for 400 epochs, a somewhat larger number than before because we're not using as many training examples. Okay, so I can do this. Training, let's only take 1,000. 400 epochs. And how does that do? It's not learning as fast, obviously. Yeah, we're still only at 80 after 12 seconds when we used to be able to get to 90 after 1 second. Using the results, we can plot the way the cost changes as the network learns. This looks encouraging, showing a smooth decrease in the cost, just as we expect. Note that I've only shown training epochs 200 through 399. This gives us a nice up-close view of the later stages of learning, which, as we'll see, turns out to be where the interesting action is. Let's now look at how the classification accuracy on the test data changes over time. Again, I've zoomed in quite a bit. In the first 200 epochs not shown, the accuracy rises to just under 82%. The learning then gradually slows down. Finally, at around epoch 280, the classification accuracy pretty much stops improving. Later epochs merely see small stochastic fluctuations near the value of the accuracy at epoch 280. Contrast this with the earlier graph, where the cost associated to the training data continues to smoothly drop. But if we look just at that cost, it appears that our model is still getting better. But the test accuracy results show that the improvement is an illusion, just like the model that Fermi disliked. What our network learns after epoch 280 no longer generalizes to the test data, and so it's not useful learning. We say the network is overfitting or overtraining beyond epoch 280. You might wonder if the problem here is that I'm looking at the cost on the training data as opposed to the classification accuracy on the test data. In other words, maybe the problem is that we're making an apples and oranges comparison. What would happen if we compared the cost on the training data with the cost on the test data, so we're comparing similar measures? Or perhaps we could compare the classification accuracy on both the training data and the test data. In fact, essentially the same phenomenon shows up no matter how we do the comparison. The details do change, however. For instance, let's look at the cost on the test data. The cost on the test data is going up. Doesn't that mean we're getting worse? We can see that the cost on the test data improves until around epoch 150, but after that it actually starts to get worse, even though the cost on the training data is continuing to get better. This is another sign that our model is overfitting. It poses a puzzle though, which is whether we should regard epoch 15 or epoch 280 as the point at which overfitting is coming to dominate learning. From a practical point of view, what we really care about is improving classification accuracy on the test data, while the cost on the test data is no more than a proxy for classification accuracy, and so it makes most sense to regard epoch 280 as the point beyond which overfitting is dominating the learning in our neural network. That's because our accuracy stops going up around 280, even though our cost stopped going down even earlier. Okay. Another sign of overfitting may be seen in the classification accuracy on the training data. The accuracy rises all the way up to 100%. That is, our network correctly classifies all 1,000 training images. Meanwhile, our test accuracy tops out at just 82.27%, so our network really is learning about peculiarities of the training set, not just recognizing digits in general. It's almost as though our network is merely memorizing the training set without understanding digits well enough to generalize to the test set. Overfitting is a major problem in neural networks. This is especially true in modern networks, which often have very large numbers of weights and biases. To train effectively, we need a way of detecting when overfitting is going on so we don't overtrain. And we'd like to have techniques for reducing the effects of overfitting. The obvious way to detect overfitting is to use the approach above, keeping track of accuracy on the test data as our network trains. If we see that the accuracy on the test data is no longer improving, then we should stop training. Of course, strictly speaking, this is not necessarily a sign of overfitting. It may be that accuracy on the test data and the training data both stop improving at the same time. Still, adopting this strategy will prevent overfitting. In fact, we'll use a variation of this strategy. Recall that when we load in the MNIST data, we load in 3 data sets: training, validation, and test. Up to now, we've been using the training data and test data and ignoring the validation data. The validation data contains 10,000 images of digits, which are different from the 50,000 images in the MNIST training set and the 10,000 images in the MNIST test set. Instead of using test data to prevent overfitting, we will use the validation data. To do this, we will use much the same strategy as described above for the test data. That is, we'll compute the classification accuracy on the validation data at the end of each epoch. Once the classification accuracy of the validation data has saturated, we stop training. This strategy is called early stopping. Of course, in practice, we won't immediately know when the accuracy has saturated. Instead, we continue training until we're confident the accuracy has saturated. Footnote. It requires some judgment to determine when to stop. In my earlier graphs, I identified epoch 280 as the place at which accuracy saturated. It's possible that was too pessimistic. Neural networks sometimes plateau for a while in training before continuing to improve. I wouldn't be surprised if more learning could have occurred even after epoch 400, although the magnitude of any further improvement would likely be small, so it's possible to adopt a more or less aggressive strategies for early stopping. Why I use the validation data to prevent overfitting rather than the test data? In fact, that is part of a more general strategy, which is to use the validation data to evaluate different trial choices of hyperparameters, such as the number of epochs to train for, the learning rate, the best network architecture, and so on. We use such evaluations to find a set of good values for the hyperparameters. Indeed, although I haven't mentioned it until now, that is in part how I arrived at the hyperparameter choices made earlier in this book. More on this later. Of course, that doesn't in any way answer the question of why we're using the validation data to prevent overfitting, rather than the test data. Instead, it replaces it with a more general question, which is why we're using the validation data rather than the test data to set good hyperparameters. To understand why, I consider that when setting hyperparameters, we're likely to try many different choices for the hyperparameters. If we set the hyperparameters based on evaluations of the test data, it's possible we'll end up overfitting our hyperparameters to the test data. That is, we might end up finding hyperparameters which fit particular peculiarities of the test data, but where the performance of the network won't generalize to other data sets. We guard against that by figuring out the hyperparameters using the validation data. Then, once we've got the hyperparameters we want, we do a final evaluation of the accuracy using the test data. That gives us confidence that our results on the test data are a true measure of how well our neural network generalizes. To put it another way, you can think of the validation data as a type of training data that helps us learn good hyperparameters. This approach to finding good hyperparameters is sometimes known as the holdout method, since the validation data is kept apart or held out from the training data. Now in practice, even after evaluating performance on the test data, we may change our minds and may want to try another approach, perhaps a different network architecture, which will involve finding a new set of hyperparameters. If we do this, isn't there a danger we'll end up overfitting to the test data as well? Do we need a potentially infinite regress of datasets so we can be confident our results will generalize? Addressing this concern fully is a deep and difficult problem, but for our practical purposes, we're not going to worry too much about this question. Instead, we'll plunge ahead using this basic holdout method based on the training data, validation data, and test data as described above. We've been looking so far at overfitting when we're just using 1,000 training images. What happens when we use the full training set of 50,000 images? We'll keep all the other parameters the same, 30 hidden neurons, learning rate 0.5, mini batch size 10, but train using all 50,000 images for 30 epochs. Here's a graph showing the results of the classification accuracy on both the training data and the test data. Note that I've used the test data here rather than the validation data in order to make the results more directly comparable with the earlier graphs. As you can see, the accuracy on the test and training data remain much closer together than when we were using 1,000 training examples. In particular, the best classification accuracy of 97.86% on the training data is only 2.53% higher than the 95.33% on the test data. That's compared to the 17.73% gap we had earlier. Overfitting is still going on, but it's been greatly reduced. Our network is generalizing much better from the training data to the test data. In general, one of the best ways of reducing overfitting is to increase the size of the training data. With enough training data, it is difficult for even a very large network to overfit. Unfortunately, training data can be expensive or difficult to acquire, so this is not always a practical option. mean, did we learn something that we can implement here? There was a stopping criteria. This is mostly just saying a lot of obvious stuff. So we could implement early stopping by checking if the validation data has saturated. Okay, so let's add to train validation data equals data.validation. We can add stopping equals early. I think we're gonna learn other stopping techniques or criteria. So for now it's just gonna be a string, but we'll change that over time, I think. So in the network, we want validation data, and we want stopping. I guess the only thing we're doing with test data okay. If validation data self.validate validation data then if we stop going up, then we should stop. So if stopping equals early and we have validation data, so we could take a window of like the last 10 epochs, and if you're if I'm not better than the average of the last 10, then I can say that I've stopped learning. So validation.append to last 10. Or that's backwards. Append validation to last 10. If len of last 10 validation is greater than 10, then you chop off the first one. And then if can I do mean like that? Does Python have that? Python mean of 1, 2, 3. No. Does NumPy have it? Import NumPy as NP. Yeah, it does. So if the average of the last 10 is greater than my current one, then we stopped learning, and we should do our early stopping, which I guess might just be to print stopping early because last 10 mean greater than validation. Does this do anything? It's gonna be hard to tell if it does anything unless I use only the first 1,000 training examples. Oh, wait. It thinks I should be stopping early. It's just not doing it. And that's fair. I forgot to do some kind of break. I mean, okay. 94% was the mean of the last 10, and then I just got 93%, so I stopped immediately. Maybe I should say median. So that I don't stop after going down once. I stop after, like, I had 5 that are bad. All right, that's fine, I guess. Like, I don't actually want to use this. Because it's not a good stopping criteria, but there, we implemented something. All right, and we'll continue with regularization next time.